Welcome, ladies and germs and other microbes, to our 7th module. Today, we will be strategizing. We will be forming an alliance of power against these electromagnetic charge distribution problems. And when I say strategizing, I mean we'll be building up a technique to tackle these systematically, to understand them in whole, meet their parents, meet their best friends, and even their dogs. So let's get right into it. I have posted an announcement about this strategy in brief, but we're going to dig out how to use it for this specific problem. So we first need a problem, which I'm going to draw under the first step, which is identify the charge distributions. A ring of charge of radius r and total charge big Q is placed a distance a away from an infinite line of charge with charge density lambda. The ring is placed such that its plane runs parallel the wire. What is the electric field at the midpoint between these two objects? And by the way, the charge on that ring is negative, because that makes the problem far more interesting. So we've drawn our system, and the problem is a little explicit here. It tells us we have a ring-type charge distribution and a infinite line type distribution. I want to emphasize that in these situations, we are not going to have to go through the whole hullabaloo of deriving the electric field of these objects every time, because that costs far too much effort. There is a shortcut way of doing this that we will not approach in this class, but believe me, it exists. So to further clarify, I want to point out that the midpoint, yoink, is somewhere right here. If this has radius r, this has density lambda, this has q, and this total distance is going to be big A. So now that we know which distributions we're dealing with, what fields arise from these distributions? We're going to be on the axis perpendicular the ring, which is helpful. Without that information, we don't have a derived electric field, so we hop on to the line perpendicular the ring, and we see that our electric field is going to be equal to this value that Sasha derived in the video. It's an ugly K. Well, you know what? Every K is beautiful. Who am I to judge? I'll even adorn this little K with a cute little flower. This K is feeling so kawaii. It loves itself. And that's what's most important in life. Self-love. And that's why we do physics. For self-esteem, that leads to self-love. So we'll notice in this situation immediately our Q is going to be negative, meaning that as our visualization would suggest, our negative charges are sucking in fields, so our field's going to be pointing in the negative x direction. Just a little observation right off the bat. Next we have our line, our infinite line, and we look that up, and we see that we get this value. I'm going to put little squigglies next to these x values, because these x values assume that our coordinate system starts at the middle of the object. So this is assuming that with our line, x is coming out, infinite line, x is coming out this way and the origin is here. And with this one, we're assuming that x is going out this way and the origin is here. So we actually need to put these two x values in either of these equations in our coordinate system when it comes time to calculate things. So next up, before we do any of that, we have to visualize this field so that we understand a little bit of how this problem is going to work. We go back to our analogy of fluorescent dye streaming out from these objects. We have this line of dye that is going to radiate outwards in all directions. So I start by drawing a little bit of that. Goes out in all directions. Okay, and it drops off its intensity as we get further away. We have this other object, this ring, that instead of emitting dye, it's a negative charge, so it's going to be absorbing dye. So we can picture that this dye is drawn towards this drain. It's being sucked sort of three-dimensionally, like towards that ring, which is like kind of hard to visualize in 2D, especially with my drawing prowess, but sort of does this kind of thing. And all of that dye gets swept away from the center of the ring. Maybe like a little bit gets through. And then on the other side, dye is also moving in towards it. Where does that dye come from? We just don't know. The depths of space, the sources of all dye. Let's throw some arrows on there. All right, so we generally have an idea of how the field is flowing through this picture. The most important part of this being that at the point we're interested in flows to the left, and it's being both pushed from the positive source of field and pulled from the negative source of field. So without a doubt, both of our vectors should be pointing to the left. Both the electric field from the ring charge and the line charge point to the left. Let's superimpose these fields. I probably didn't need that much space for that, but if it were a more complicated setup with vectors pointing in different directions, I would. This looks similar to our free body diagrams, where we move from each individual force to our net force. So superposition allows us to do the same thing in that our net field at the point is just the sum of each individual vector. To figure out what these vectors are in algebra, we need to be careful about our coordinate systems. So when I'm doing this, I'm going to go back up to my picture, and I'm going to say, all right, how does the magnitude depend specifically on the coordinates I've chosen? So I'm going to draw this up here. We have, well, okay, what do we want to choose? Do we want to choose the line charge to be the origin, or do we want to choose the ring charge to be the origin? Flipped a coin, mined coin, flip that mined coin, and I chose this one. Congratulations. That's what we're doing. So our x-axis starts right here. So that means that our quite kawaii equation E ring is already valid. That x is the x that we chose. Our line charge equation is a little less valid. So we want to figure out this distance, which we were previously calling x for the line charge, and now we're going to call it what it is in this coordinate system. So we see that the distance that's actually x is right here. And if we know that to be true, and this total distance to be a, that means that our x is going to be equal to a minus x. We answered the age-old question of, where even am I, man? That is where we are. Using that information, I'm going to update this to say a minus x. And that way I can put that directly into here as the magnitude of that field. Just updating it so that every point along the way is consistent. And finally, I write those as vectors together. And knowing that they're both pointing in the negative direction, I'm just going to write minus E ring magnitude and also minus E line magnitude. So both of those will have a negative contribution to the total field. Hooray! Now, because we're looking for a specific point, a specific E total, and there may be numbers to plug in here depending on the problem, I trust your ability to do algebra, so I'm not including that in this problem. This can be written for x equals a over 2, our midpoint. Oops, I forgot. Made a little boo-boo. Perfect. That sure doesn't simplify things very much. And sometimes you just get a slightly unaesthetic answer. But you can fix that pretty easily. Stellar. Okay. Now, does this answer make sense? Interpret our results. So in general, this result interpretation can be a little more complicated than this one, but in this case, we had a relatively simple field because everything was on the same axis. So I look at E total, and I could ask some questions about it. I could ask, in what direction is it pointing? K, Q, A, R, and lambda are all positive, and they're being subtracted, meaning that we have a negative total. And this simple direction corresponds to what we predicted there, what we predicted here, and our whole kit and caboodle. It's a very self-consistent situation. The actual size of this field is a little bit up in the air, but we can tell, well, it's kind of made up of the two fields. Like, nothing really canceled out. We have, apart from the ring and apart from the line, working together to create our total field. They are superimposing and both working together. So even if it's algebraically a little messy, we could just plug in the numbers for our known values and determine what the field is. And that's often how these problems boil down. Even if the algebra looks gross, we still have a reasonable looking field, and that's what counts. In conclusion, even if these problems have a little bit of hideous looking forms, all you really need to do is what we did. We could have added more lines, we could have added more rings, we could have added some point charges if we wanted to. We just start out with identifying the charge distributions, know your new friends. You figure out what fields come from these distributions, which we just looked up. Don't do any of the gnarly calculus, at least not in terms of that weird integration. We visualize the field using our advanced tablet technology or your advanced brain technology. We superimpose the fields at the point of interest very similarly to our free body diagrams and turn that into our beautiful algebraic form, which we made beautiful through the power of imagination and kawaii flowers. Then interpreted that it points in the negative x direction, as is consistent with the rest of our problem. So there we have it. Another day, another electric field visualized. Good going.
I fell into a burning ring of fire. I went down, down, down.